Hello everyone, welcome to our final thesis presentation. Our topic is on the detection of intracranial hemorrhage on CT scan images using convolutional neural networks. First, let me introduce you to our team, where we worked under the supervision of Dr. Zavid Pervez sir and Dewan Ziol Karim sir. Our team consists of Afridi Ibn Rahman, myself Subhi Bhuiyan, Ziad Hasan Reza, Jasarat Zaheen, and Tasin Nahian Khan. For the presentation outline, I will start with an introduction of our topic and discuss related works in this field. Then Jasarat will present the data that we worked with. Next, Afridi will demonstrate how we developed the model. Then Reza will talk about the experimental results to evaluate the model. And finally, Nahian will discuss and conclude the presentation. Now I will begin with the inspiration behind choosing this topic. Stroke is a leading cause of permanent disability and death. According to the World Health Organization, nearly 15 million people worldwide suffer from stroke every year. Stroke is broadly classified into two categories, ischemic and hemorrhage. And we are particularly looking into intracranial hemorrhage, which is essentially a bleeding within the skull of the brain when a blood vessel is ruptured. This brain damage can be minimized if it is diagnosed immediately. But it turns out that 2/3 of the global population lack proper access to advanced stroke diagnostics and specialists. And this is why we wanted to incorporate applications of artificial intelligence in the healthcare domain so as to enhance medical care. Learning has shown potential to provide data-driven clinical decision support based on artificial neural networks. And we are using CNN, which is a deep learning model because it is effective and gives accurate results. And it is also capable of outperforming humans in image classification. The two modalities regularly used for stroke diagnosis are CT scans and MRI. But since time is a crucial factor, we prefer to work with CT images as it has the advantages of speed and cost. Our brain is the most complex organ in the human body, and we wanted to address the challenge of a life-threatening medical emergency and figure out how integrating an application of AI can help to improve clinical diagnosis. This influenced us to work on the detection and binary classification of intracranial brain hemorrhage on CT scans. We employed convolutional neural networks and its transfer learning approach. And for that, we have trained 7 CNN models, one 11-layered traditional model, and 6 pre-trained models. There has been significant research done on this particular field, and I'll talk about 3 recent research that has been done on the same dataset we worked with. The study done by Hasan et al. In 2020, they were the first to develop and release the dataset. In their research, they employed UNet, which is a fully convolutional network to detect intracranial hemorrhage, and achieved an accuracy of 87%. In the same year, Anupama et al. Developed a Brac-based segmentation with synergic deep learning named GCSDL model that can detect intracranial hemorrhage images in wearable networks. Their proposed method used Gabor filtering to improve the image quality by noise removal and attained an accuracy of 95.73%. In another research, Chen et al. Presented a smart IoT-based application for hemorrhage classification using machine learning algorithms. In their paper, the accuracy obtained was 80.67% for support vector machine and 86.70% for feed-forward neural network. To summarize, here is an accuracy review on this dataset. We have taken inspiration from these studies and then proposed to work with 7 different CNN models, and then suggest a comparative analysis on the performance. Turns out, one of our pre-trained CNN models named EfficientNet P6 gave the highest accuracy of 95.99%. Now Jasarat will talk about the dataset we worked with.
Assalamu alaikum, this is Jasarat Zaheen. I am going to talk about the dataset we use for our thesis. The dataset has been collected from PhysioNet repository. Our retrospective study was conducted from Al Hilal Teaching Hospital, Iraq, between February and August 2018. From the study, a total of 5001 images are collected from 82 patients, which means 30 images per patient were collected on an average. Data organization. A total of 5001 images are accumulated, among which 2501 images are of brain CT scan and rest 2500 images are of bone. We discarded the bone image as we only need the images of brain CT scan to train the CNN model for our research, among which 1104 CT scan were of hemorrhage and 1397 were normal brain CT images. Subject demographic table. So total number of subjects are 82, among which 46 were male and 36 were female. Their age range were 19.5 to 27.8. Let's move on to the dataset splitting. We splitted the dataset in this ratio 70, 20 and 10 for training, validation and testing respectively. For training, total number of 1801 images, of which 825 were hemorrhage image and 1426 normal image. Its percentage is 70% approximately. For validation, total number of images is total number of images are 450, of which 225 hemorrhage image and 225 normal images. Its percentage is 20% approximately. For test part, we have total number of 250 images, of which 125 normal images and 125 hemorrhage images. Its percentage is 10%. Train and validation percentage isn't completely accurate because the number of CT scan for each patient wasn't the same. For example, patient A has 33 CT scan but patient B has 26 CT scan, so even distribution wasn't possible. We also ensured there was no overlapping. Let's move on to the pre-processing part. Our pre-processing consists of two parts: image resizing and image augmentation. We resized all the images to 224 by 224 as most architecture downsampled this input size, and the batch size was 32. In data augmentation, we applied the following transformation to the training dataset using Keras image augmentation library, which includes random flip, random zoom, random crop, and random rotate.
Hello, Assalamu alaikum. My name is Afridi Ibn Rahman. I will describe the model development procedure of this research. As we have mentioned earlier, we are using convolutional neural network CNN to detect intracranial hemorrhage on head CT scan images. The algorithm CNN is best known for recognizing and classifying images because of its high accuracy rate. In order to classify images, CNN performs better than many popular machine learning algorithms including ANN, RNN, LSTM, MLP, and SVM. Hence, we opted to go with CNN. For developing the model, we have divided our work methodology into 5 parts. It starts with building our 11-layer CNN model. Then we load the pre-trained CNN models. After that, we add some optimizations with a view to achieving better performances from the models. Then we add hyperparameters to have a detailed understanding of the performances. Then we observe and evaluate the performances. And finally, we deploy a web app using the best performing model. While developing the model, we at first proposed a new 11-layer CNN model. Basically, there are 3 types of layers that make up a CNN model. They are, as shown here, the convolutional layer, the pooling layer, and the fully connected layer. To briefly describe about the layers for our proposed model, we at first selected 4 Conv 2D layers at convolutional layer. Similarly, 4 max pooling 2D layers have been used for the pooling layer, and finally, the fully connected layer is composed of 1 flattened layer and 2 dense layers with sigmoid activation function. And this is how we have built our 11-layer CNN model. After building the 11-layer CNN model, we load another 6 pre-trained models for transfer learning. In order to do so, we used the popular Keras pre-trained CNN library. The library has many well-known CNN models such as the VGG, the DenseNet, the ResNet, and many more, including different versions and variants of those many models. Like the Inception, it has 3 versions: Inception V1, V2, and V3. Keras offers all of them. While selecting 6 pre-trained models for our research, we tried to keep at least one version from these many models in order to make our selection as versatile and as diverse as possible. So from the VGG, we took VGG 16. From the DenseNet, we took DenseNet 121, ResNet 50 from the ResNets. From Inception, we took Inception V3, the Fusion Inception ResNet V2, and finally EfficientNet B6. This is how we have completed our selection for the pre-trained CNN models. For optimizations, we used a dropout of 40%, then regularization types of both L1 and L2 to make sure that there isn't any overfitting in the models when they get trained. Finally, in order to make the neural networks learn faster and achieve better performance, we used Adam replacement optimization algorithm. So, this was all for the model development.
Hello, My name is Ziad Hasan Reza and I'm going to discuss the model evaluation part. Now, in order to evaluate the models, we used a few performance metrics which are accuracy, precision, recall, and F1 score. Accuracy is the ratio of total correctly predicted cases and the total number of cases. Precision is the ratio of total correctly predicted positive cases and the total predicted positive cases. Recall is the ratio of total correctly predicted positive cases and total positive cases. F1 score is the weighted average of precision and recall. Now here we can see that EfficientNet B6 has the highest accuracy of 95.99%, followed by DenseNet 121 with an accuracy of 95.59%, and then ResNet 50 with an accuracy of 94.4%, Inception ResNet V2 with an accuracy of 90.79%, Inception V3 with an accuracy of 87.99%. VGG16 has a low accuracy of 70.8% and traditional CNN model performed poorly with an accuracy of only 50%. We also used AUC or area under the curve, which is a measurement of the ability of a classifier to differentiate among the classes. In this graph, we can see that EfficientNet B6 has the highest AUC score, followed by DenseNet 121, ResNet 50, and Inception ResNet V2. VGG16 and traditional CNN model has a poor AUC score. Now we have the confusion matrix where we can see the number of true positive, true negative, false positive and false negative cases identified by each model. Here EfficientNet B6 has a high number of true positive and true negative cases and a very low number of false positive and false negative cases. Then DenseNet 121 also has a high number of true positive and true negative cases and low number of false positive and false negative cases, similar with ResNet 50. And at the bottom we have VGG16, which has a high number of false positive and false negative cases and the low number of true positive and true negative cases. The traditional CNN model also performed very poorly here. Here we have a summary of the confusion matrices and we can see that EfficientNet B6 has the lowest total number of false positive and false negative cases. DenseNet 121 also has a very low number of false positive and false negative cases. And VGG16 traditional CNN model has a high number of false positive and false negative cases. That's all from me. The next part will be discussed by Nahian. Thank you.
Hello everyone, I am Tasin Nahian Khan. To wrap up this presentation, I would like to mention that we developed intracranial brain hemorrhage detector with EfficientNet B6 model, which as we know is our best performing model. We tried to keep the application very simple and easy use of access. The website takes CT scan images as input to detect or differentiate between healthy brain images and the hemorrhage images. Now if we move on to the next slide, we used Python 3.6 TensorFlow 2 Flask given at the back end to run the software. We have also included scikit-learn and scikit-image libraries to process the image input. The website was built on local machine, later hosted on Heroku, which is a cloud platform. User interface of the website is very responsive and very lightweight, with the help of Heroku's standard one-time dynos consisting of 512 megabytes of memory, which allowed us to have the user not requiring any further processing power. Generally, the ad gives output within just 4 to 10 seconds. Most important of all, the application does not record any user history, and this in turn helps to secure patient confidentiality. Now I'll show a very short demonstration of the website. As we can see, the website is very lightweight, and now if we choose pictures of a hemorrhage image from our test dataset and we predict, we can see that the result is expected, which is hemorrhage. Also again, if we choose a normal image from our normal test dataset, and here we're choosing a normal image, and if we predict again, we can also see the result will come according to our expectations, which is normal. So we can see that our application is working. And if we move on, our aim is to aid doctors to make faster and precise diagnosis, for we have trained 7 CNN models and proceeded forward with the best one, and in fact we were able to achieve an accuracy of 95.99% from EfficientNet B6. We hope to improve clinical diagnosis and efficiently diagnose intracranial hemorrhage. Like any other system, our model has few limitations. Model lacks to incorporate patient history and data itself is coherent, and results can lead to misdiagnosis. Also, the dataset lacks supplementary information. To conclude, I can briefly say our model uses CT scan images to binary classify between hemorrhage and non-hemorrhage images using efficient B6 as the base model. In future, we would like to implement multi-class classification and use ensemble techniques to obtain better predictive performance. We would also like to widen our research to other parts of the brain and train models. Thank you.